Hello, everyone. Bolted is a bare metal cloud architecture to support security-sensitive tenants. Security-sensitive tenants are entities such as hospitals or financial institutes that have both the expertise, desire, or requirement to trust their own security arrangements over those of a cloud provider. This work is a collaboration between the Mass Open Cloud and our industry partners. There are several problems with existing clouds for security-sensitive tenants. First, virtualized clouds collocate multiple tenants to a single physical node, exposing tenant to side channel and covert channel attacks. Also, malicious tenants can exploit vulnerabilities in the hypervisor to launch attacks against other tenants and the provider itself. Second, popular cloud management softwares like OpenStack can have a trusted computing base with millions of lines of code and a massive attack surface. Third, the existing clouds are black boxes, providing tenants with very limited visibility and control. The tenant, including security sensitives with deep expertise, need to fully trust that the provider is doing everything right from security perspective. Finally, for operational efficiency, cloud providers tend to support one-size-fits-all solution, where they apply uniform solutions like network encryption to all customers. Different security-sensitive tenants can have different security requirements. For example, defense agencies may need two independent layers of encryption, while HIPAA doesn't require it. In addition, by definition, most tenants are not security-sensitive tenants. And if the provider deploys a very strict security solution, it may hurt the performance of the other tenants. While bare metal clouds eliminate the security concerns implicit in virtualization, they are not addressing the other challenges that I described in previous slides. For example, OpenStack's bare metal service still has all the OpenStack in its TCP. Also, bare metal clouds are vulnerable to a class of firmware-based attacks. So the question is it possible to have a cloud even suitable for security-sensitive tenants? Is it possible for this kind of tenants to not fully trust the provider? And is it possible to achieve this without sacrificing the performance of the other tenants? We developed an architecture for bare metal cloud, Bolted, which demonstrates that to answer to all of these questions is yes. Bolted has three main microservices that tenant interacts with them through a user-level script. Isolation service can be used by tenant to allocate node and network. Provisioning service is used to load operating system and software on the node. And attestation service allows tenants to measure firmware and software into a TPM crypto processor and then compare these measurements against a whitelist to make sure that the node is not compromised. Here how it works. The tenant uses the isolation service to get a free bare metal node. Then she creates an isolated environment that we call airlock, where she can make sure that the software running on the node, including firmware, is not compromised before she puts the node into her secure network. Using isolation service, she puts the free newly acquired node into the airlock. Then, using provisioning service, we download attestation services client side on the machine, and we attest the software and including the firmware running on the machine against a whitelist residing in the attestation services server side. If the node passes the attestation, tenant puts the node into her secure network and provision it with operating system and application. If not, tenant rejects the node. We have developed a prototype of bolted architecture. Hardware isolation layer, or HIL, is our implementation of isolation service. A tenant can invoke HIL to allocate nodes, create network, and including management network, and connect this network to any provisioning tool. HIL controls provider's switch to provide VLAN-based isolation. Therefore, tenant cannot deploy the HIL because it needs to have privileges. So it must be deployed by the provider. To minimize the TCP, we tried hard to keep HIL very simple, and it is implemented in 3,000 lines of code. Bare metal imaging, or BMI, is our implementation for provisioning service. BMI serves images from iSCSI-based network-mounted boot drives, and with a backend self-distributed storage system. As a result, there is no need to scrub the node before releasing it. When the node network boots, it only fetches the part of the image that it uses, and it is usually less than 1%. And this significantly reduces the provisioning time. Keylime is our implementation of attestation service. It is a remote attestation and key management system. It delivers tenants key kernel, initiality, encryption keys, and flow controlling scripts. So, fundamental goal of our system is to provide flexibility so that tenants only pay in performance and cost for the security they need, while security-sensitive tenants can take full control of their own security. To show how we do this, let's walk through a simple example. Imagine we have a security-insensitive tenant, Alice. She can be a graduate student, for example. She uses provider's isolation service and provisioning service and runs her applications as fast as possible. Now imagine we have security-sensitive tenant, Bob, who is willing to trust the provider, but not other tenants who may have used the machine he's using and compromised it before. So he uses provider's attestation service to make sure that the node is not compromised. In addition, we have Charlie here, who is security sensitive, and he doesn't trust not provider or other tenants. But he doesn't have any choice other than using provider's isolation service. Because as I said before, isolation service has to have the privilege to work with network switches to implement network isolation. So he needs to use that. But he has the expertise to deploy his own security procedures, including provisioning and attestation services. Bolted components can be any system with required features. Here, for example, provider uses HIL, BMI, and Keylime to deploy his own security policy. On the other hand, Charlie uses Foreman, which is a popular provisioning tool, and it is used by many enterprises for provisioning. And he uses Keylime, possibly with some modifications, to answer and address his security requirements. As I explained in the previous slide, if a tenant doesn't trust other tenants, he can use provider services. If he doesn't, he needs to deploy his own services. But it is not good enough, right? For example, if the because provider, for example, can see all the traffic going through the network. So he needs to do more than deploying own services. The first thing that he needs to do is encrypt the network. In our implementation, we have used Keylime, and Keylime supports automatic configurations of IPsec for network encryption. And this is happening using key bootstrap during attestation, and it is bound to TPM's hardware root of trust. Second thing that a tenant, security-sensitive tenant needs to do is to encrypt a disk, because to remote disk, actually, because the provider has access to the raw volume. In our implementation, we have used Linux Unified Key Setup, and we have integrated locks with keylime, which bootstraps keys during attestation. As we explained before, bare metal clouds are vulnerable to firmware-based attacks. Existing BIOS and UEFI are complicated code with large attack surface. They are opaque and they are vulnerable, and the tenants cannot check them, verify them to see if they have vulnerabilities or not. Even they can't check that if the latest patch is applied or not. To address this problem, one of our co-authors at 2 Sigma has developed Linux boot. It is based on Linux, so it is open source and scrutinized by many users. More important, Linux boot is deterministically built, which means that tenant can download the source code, compile it, and measure it, and then compare this measurement against the measurement of the firmware running on the machine, and make sure that the firmware running on the machine is exactly the firmware that he expects to be. We have used Linux boot as an execution environment in our execution environment, for attestation client. Having Linux boot burned into the server's flash RAM, we directly download keylime clients on the machine and run it. For the servers that we can't put Linux boot on, which frankly is most of our servers, we are using UEFI for minimum amount of time to download Linux boot's runtime and then follow the same steps as before. And it was a very cool thing to do, burning the Linux boot into flash RAM. What is the cost of having a secure cloud? In this figure, we show Foreman, which installs Fedora, reboots the server, and boots from the local disk. In environment, it takes around 700 seconds. And this number is very optimistic because many bare metal services are taking more than this because of the extra steps they are doing. For example, scrubbing disk. Sorry. For the case that tenant doesn't care about the security with bolted, he can use heal and BMI, which takes 300 seconds in our environment. This time is dominated by UEFI's post time. We introduced network mounting for the drives to avoid scrubbing the node before releasing it. But it actually resulted in a great performance gain because it downloads a small fraction of the image it uses. For the users who care about security and are willing to trust the provider, but not other tenants, they need to go through the steps that I discussed before. For example, putting the node into airlock, attestation, moving the node to the secure network, and KZking into the kernel. And all this process takes time. But, excuse me, I forgot. But even in that case, bolted is faster than standard format. In the case that the user doesn't trust the provider, disk encryption and network encryption adds more overhead. Even in that case, we are faster than, again, format. In the case of our own firmware Linux boot, our time is around 170 seconds. And this time is comparable to virtual machine-based cloud. And this is because the short time that Linux boot has for the post. For the same reason, actually, we for like network-mounted disk, we developed Linux boot to have better security, but it resulted in a better performance because of the short time that it has in the post time. For the users who are not trusting other tenants, our time is faster than UEFI's all cases. And one of the reasons is the post time, and the other reason is that we have reduced the number of steps to attest the node, required to attest the node. Again, for the users who are not trusting the provider, with logs and IPsec in the place, our performance, again, more than 2 times faster than 4-man. These results show that, sorry. Okay. To show the overhead for applications when the tenant doesn't trust the provider and needs to use network and disk encryption, we have run several macro benchmarks. First, we run applications from NAS parallel benchmark. For compute-intensive applications, like embarrassingly parallel, the overhead is small. But for network-intensive applications, such as MPI conjugate gradient, the overhead is as high as 210%. These results suggest that there are definitely workloads for which not trusting the provider doesn't incur a very huge overhead. On the other hand, deploying and using one-size-fits-all solution is inappropriate. Only tenants who are willing to trust a provider are likely to use to run network and I/O intensive applications in the cloud. Our next experiment is a typical cloud application running Terasort on a Spark framework. We see around 30% overhead, and even though it is a significant overhead, we are expecting that security-sensitive tenants are willing to incur this level of overhead. These results show that based on the tenant, their requirement and their applications, security overhead can be different. And this should be the tenant who chooses the trade-off between cost, performance, and security. You can check the paper for more results. This work has moved beyond a proof of concept. Keylime is going upstream into Fedora and is on the RHEL roadmap. HEAL and BMI are getting integrated to Ironic, and Linux boot is getting adopted by open compute vendors. We discussed bolted architecture for bare metal cloud. Bolted has demonstrated that it is possible to measure all components needed to boot a server securely. It consists of small micro benchmarks, which enables tenants to minimize trust in the provider. In addition, a provider doesn't need to deploy a one-size-fits-all solution. In that way, security-sensitive tenants can deploy their own microservices and fulfill their security requirements. And we show that security can have different overheads based on the tenants and their requirements and their applications. And it should be the tenant who chooses the trade-off between cost, performance, and security. Thank you.
Your attestation service uses a whitelist-based approach. Did I get that right?
Yes.
So, I mean, whitelist-based approaches are difficult to scale up and difficult to maintain. Can you comment on why you wouldn't use some other approaches like static analysis of the firmware to attest it?
We have several reasons. One of the reasons is that we are using this attestation service for I didn't describe it here, but we are, for example, we are using it for continuous attestation for runtime. So user can have this whitelist and update this whitelist for his applications. So attestation service can check the applications that are running in the the user's operating system to be sure that it's not compromised, even in that case. So we wanted to have something dynamic to support these features.
Hi, John Crizzle, University of Rochester. So if I understand correctly, the hardware isolation layer is a mechanism provided by the cloud provider to ensure that the bare metal machine cannot be accessed by any other network host while it is being provisioned. If that is the case, if my understanding is correct, then how can the client ensure that the hardware isolation layer is actually doing that, right? Because the client doesn't really want to trust the provider in any way.
So your question is that we need to be sure that isolation service is working correctly, right?
Correct.
Okay. Hardware isolation layer is in our trusted computing base. We need to trust that. We have tried, as I said, we have tried it to make it small, 3,000 lines of code. But we need to trust at that minimum trust in the provider. We are not eliminating completely the trust in the provider. It is minimized trust.
Okay, thank you.
Judges, hi, Texas A&M University. I want to ask, so a lot of hardware features need OEM or off-the-shelf firmware to use it. So I just wondering, since you're using open source firmware, wouldn't that affect the usability of the system? You cannot use this hardware feature anymore.
So you're asking about the firmware, it is being used in other systems or not?
That's true.
Okay, Linux boot right now is used in Open Compute project, which is funded by Google and Facebook. For example, it is used in Open, what was the name? Leopard servers. And I think it is used in Chrome servers too, Chrome books machines too. But yes, it is very difficult to make vendors to use Linux boots. So that's one of the challenges we have. Yes.
I think you want to add the reliance on it.
Exactly. Yes. 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 As I showed that we can use UEFI as the base firmware, run it for a minimum amount of time, and download Linux boot's runtime on it. Actually, let me. I can show you
maybe
the process.
That's okay. So I guess part of my question is is there hardware feature, for the CPU feature that you cannot support through these open source Linux boot?
Actually, sorry, I am.
So is there any CPU features that you cannot support?
Okay, when we are compiling Linux boot, we are not compiling it from the scratch. We are downloading the BIOS or UEFI out of the flash ROM. The figure I showed here. We first download the firmware out of the machine, extract some part of it which is specific to the processor, and embed it into the Linux boot's final image. So for example, Dixie is in that image. We have extracted it out of it.
Let's continue to the next question.
Ed Bugnon, EPFL. So servers typically have this very pesky, annoying feature, but necessary in many cases, called the BMC, which is a little computer next to the computer that basically allows you to connect it out of band, and it's used for a number of operations. And so I guess my question is, do you assume that you have a BMC and you somehow secure access to it, or do you assume that you do not need a BMC?
Actually, that's one of our great challenges right now. Not only BMC, what about IMMU, what about management engine, what about power? That's the open question for us. We need to consider that.
Hi, Amin, nice talk. So how large is firmware?
This firmware,
I mean, in general, how many lines of code is firmware?
it's a stripped down Linux boot. The whole image, the final image itself is compiled one, is around 32K. But because we are extracting some part of the image out of this, the whole final image is for servers is 16 megabytes. For laptops that we use, it was 4 megabytes, as I remember.
I don't know if I what's typically firmware size, I was asking, not your image size.
I see. For this one, when we downloaded the original image, it was 16 megabytes. So we had to pad the whole image to make the same size. So, for example, bootguard wouldn't complain about the differences.
I think what I'm trying to get is that, like, trusting 3,000 lines of code, which is the 8IL plus keylime plus you had another couple of things there, might be actually a bigger trusting computing base than the firmware itself that you don't trust.
Keylime and
maybe I'm asking.
No, Keylime and BMI are not part of trusted computing base. They are deployed by the the tenant himself, right? So they are not part of the trusted computing base. The trusted computing base for our case is Hill, which is 3,000 lines of code. The Linux boot, the firmware, and I think these are the main parts of the trust.
Right, so I don't see why the argument that trusting this is actually better than trusting the firmware in the provider itself. Well, yeah, I understand, but you also trust the 8IL, so why not? Why the other rather than the other?
Okay, let's.
You want to speak too, right? Mm-hmm.
Okay. Let's thank our speaker
thanks.
again. And